This is experiment 13 from Physics with Vernier. The lab is called air resistance. In that lab, we take a coffee filter and drop it and observe it as it falls with constant velocity, like this. Because the filter is falling with constant velocity, we know the net force on it is zero. In other words, the weight and the air resistance forces exactly cancel each other out. Now, air resistance is an interesting thing. It's zero when the filter is not moving, but it clearly increases to a different value as the filter speeds up. Exactly what is that function like? Well, you could model it with a linear function where the air resistance is just proportional to the velocity, or it might be a quadratic function where the air resistance is proportional to the square of the velocity. Those are two different models. We can actually do an experiment and test them and see which one is closer to reality. That experiment involves a motion detector and a Labquest and a couple of coffee filters. Here's a hint that's not in the book. I like to reverse the coordinate system so that up is positive even though the motion detector is pointing downward, and then zero it so that it reads zero at floor level. I'm going to do that now. So I'm going to reverse it, and I'm going to select zero when nothing is under the motion detector, and that means that the system is going to read zero at this time. When I hold something under it, it's reading now 1.5 meters because I'm 1.5 meters above the floor. Now, I'm going to take a single coffee filter and start data collection and take my hand away, let it fall. Now, if we take a look at the graph, you can see that in this part of the graph, I was holding the filter steady, then I let go and the filter started falling and speeding up, but then the velocity reached a constant value. You can see that because of the linear slope of this position time graph. I can extract that terminal velocity very easily by selecting a region of my position time graph and doing a linear fit. So I've selected it, I can go to the Analyze menu and ask for a curve fit on the position graph. And I can choose the linear fit, and I see that I've got a slope of about 1.04 meters per second. I can tap OK and get that on the main graph. So there's the terminal velocity for one filter. If we do that experiment with two coffee filters, same physics, same method, start data collection, you see that the terminal velocity is a little larger, indicating that the terminal velocity is slightly larger for two filters. After I collect data for 1 through 8 filters, I can take those data and regraph them. Because a stack of 2 or 5 coffee filters has exactly the same shape, it's easy to measure the terminal velocity for objects of exactly the same shape, but 1, 2, 3, 4, 5 steps in mass. If we then make a graph of the terminal velocity as a function of the number of coffee filters, we can test that model. If we use Newton's second law, coupled with our two models, one which says the drag force is proportional to the velocity, and the other which says the drag force is proportional to the square of the velocity, we can do a little bit of algebra and find that the first model predicts that the terminal velocity should be proportional to the mass. The second model, with the quadratic drag force, we find that the terminal velocity should be proportional, the square of the terminal velocity should be proportional to the mass. That's something that we can test. So now, given our collected data with terminal velocity measurements for a variety of numbers of coffee filters, we can graph it two different ways: the terminal velocity versus mass and the square of the terminal velocity versus mass. One of those, or neither one, may be a line of proportionality, and if one of those follows a line, then we know we've got a good model for the air resistance force. What I've done here is use the Labquest app with no sensors connected. In the X column, the data table, I have entered just integers representing the number of coffee filters. In the next column, I have entered the terminal velocities for each number of coffee filters. So these terminal velocities all came from the slope of the line fitted to the linear portion of the position versus time graph. Let me show you how you can use the features of the Labquest app first to label the columns a bit better than X and Y, and then also to create a column that is the square of the terminal velocities. As I said, this first column is simply the number of coffee filters, or it's proportional to the mass of the stack. If I tap on the X, that calls up a dialog where I can control the settings for that column. The name of the column is X, but I can select that and just change it to M. And I can tap OK, and now my column is named M. If I tap on that Y, I can rename that as, oh, say, VT, meaning terminal velocity. And I could enter units. I'm going to keep going. Now, I've got my mass and terminal velocity columns. Now I want another column that is the square of the terminal velocity. From the table menu, I'm going to choose New Calculated Column. I'm going to give it a name, be the square of the terminal velocity. So how about VT, and then to the second power, representing the square of the terminal velocity. Then I need to create a rule for calculating this column. I need to select an expression from this drop-down field here. And if I scroll down a little bit, I'll see ax to the b power. If I choose that and scroll down a little further, I can see that I can change values for a and b. And ax to the b power, I just want a to be 1, and I want b to be 2. And I can tap OK. And let me go back to my data table. And there, I've got a column that is labeled the square of the terminal velocity, and each of these values is simply the square of the contents of this middle column. If we look at a graph of the square of the velocity versus mass, we see that the line looks pretty straight. Let me change the graph, though, so that it includes the origin, since we're testing for proportionality. You can see that the horizontal axis goes from 1 to 8 rather than from 0 to 8. If I go to the graph menu and choose graph options, I see that the left bound, it says 1. I want that to be 0. And I'll tap OK. So there's my graph of the square of the terminal velocity versus mass. Let's also look at the graph of the terminal velocity versus mass. If I go to the graph menu again, I can ask to see a couple different graphs, 2 graphs. Oh. Here then is a graph of the terminal velocity versus mass. Both of them look pretty straight, but if we fit a line of proportionality to these, you can see very quickly that one of them follows the proportional model and one doesn't. So let's take this one, go to the Analyze menu, go to Curve Fit, and fit a line, a proportional line, to terminal velocity versus mass. So I'll choose the proportional fit, not the linear fit, because those are 2 different things, and tap OK. And I see that my proportional model doesn't follow the terminal velocity data at all well. Now, let me swap over to the square of the terminal velocity. Once again, I'm going to change the graph range. To include the origin, and let's do a curve fit. Again, I'm going to use the proportional model. And this time, I get a pretty good fit for the square of the terminal velocity versus mass. This tells me that the model with the drag force being proportional to the square of the velocity is much closer to reality than a model with the drag force being merely linear with velocity. So this experiment has helped us to choose between 2 models for air resistance, one with the drag force proportional to the velocity and the other with the drag force proportional to the square of the velocity. In reality, the drag force is more complex than either one of those, but for the purposes of the falling coffee filter, the quadratic drag force model looks to be pretty good.